Welcome to Programming in Modern C++. We are going to discuss tutorial 7. It will be on how to design a user defined type that behaves like a built-in type. This is the first part where we will discuss about a user defined type fraction. Right? So, that is the basic objective. And this is the outline which will be there on the left. Now, before we get into this design, let me remind you of a few things that you have done in the modules so far. You have seen that there are several data types in C++ which are used to specify the type of data constants as well as data operations that we use in our program. And if we look into the different categories of data types that are available to us, certainly there are a number of primitive or built-in data types like char, int available to us. There are derived data types which are built on top of these like arrays, structure and so on. And then there are user defined types. User defined types are the pure addition and one of the strongest features of C++. So, in built-in types as we have different kinds of char, int, float, bool, even we have void. In derived types arrays, functions, even references we have. In user defined types, the user has the liberty to define the set of nominal values of the data type as well as its operations and its properties, axioms, so to say. And this becomes really useful because now you do not need to rely on a whole lot of functions that you had to write in C to realize the functionality of the type of data that you are dealing with, but you can build for a particular concept of a data type, you can build it pretty much like the built-in types that we have. So, we have often taken example in different places in the module of operations being done on the complex type, right, like add, subtract, multiply, divide, take conjugate of and so on and so forth. In fact, conjugate type is also the complex type is also available in the standard library. In addition, we can ask for a fraction type which deals with fraction and does several algebraic operations. There could be matrix types which deal with matrices, their addition, subtraction, inversion, square matrices, vectors and so on and so forth. There could be a set type for union, intersection, difference and so on. There could be several other types like a polynomial type, there could be a rectangle type, right. Now, the basic point here is that when you program with such entities in C, you necessarily write a bunch of functions and you have to manage the data between these functions. But here using the tricks of user defined type definition and build up, you will be able to build a type which behave almost exactly as your int type or your char type and so on. You can do direct IOs with them and so on. So, the main objective here is to illustrate the process of building such a user defined type using a fraction type, because that is known to all of us. So, what are the issues involved in this design? To design a UDT fraction which will behave like an int, the broad tasks, first task would involve that we need to have a clear idea about the concept of fraction. What we mean by fraction? We must be clear about that. We must identify a proper representation of a fraction object in the system, in the memory, right. So, representation is important. We have to identify the properties and assertions that are applicable for all objects. What is a valid object, what is not a valid object, and so on. And finally, we need to identify the operations for the fraction objects, right. Once we do that, then we will be able to go towards the design of a fraction UDT. Now, obviously, for the operations, you have to choose the appropriate operators to overload. You could just use member functions for doing different operations, but we will see why having overloaded operators will really help. And when you make such a choice, you have to be careful. For example, you could choose operator plus to add two fractions, or operator output streaming to stream a fraction object to C out. But be careful not to break the natural semantics of the operator. What I mean by that, for example, you say operator plus, but actually you are trying to do a multiplication of two fractions. Do not do that, because that breaks the meaning and the overall value of making a UDT loses, because the whole idea is looking at the operator, user should be able to identify without any documentation or anything as to what is intended. So, when we talk about string type UDT, which is there in the standard library, we say that operator plus basically means concatenation, and certainly some operators may not be defined for a certain UDT, like for a string type operator minus probably does not make much sense. Now, the question is how should you go about doing the design? Would you be able to conceptualize everything, work out every details and put down a design in one go? Yes, if you are an expert, you will be able to do that. But the whole purpose of this course, such tutorial, is to create the expertise. So, what I am going to illustrate is not a one shot design and go, but we will go by what is known as iterative refinement. That is, we will make a design which is more or less okay. We will implement it, test it, identify the shortcomings, and then refine and repeat this process. Here in this tutorial, I will show that at least in two stages. So, first the notion of the fraction. Every one of us understands what is a fraction, which is a number of the form p by q, where p and q are integers. The important thing about fraction is it has a non-unique representation, that is 2 by 3, 4 by 6, 8 by 12, minus 2 by minus 3 all mean the same fraction. Similarly, all of these. So, that is something which is going to create a lot of problem in terms of a UDT, because how will it represent in the system, how will I represent it when I stream it to the output and so on. So, what we need is we need to uniquify the representation. We need to make the representation unique, and for that we do two things. One is, out of p and q, we make q necessarily positive, that is, the denominator cannot be a negative number. This is the assumption we make, and we make that p and q must be mutually prime, that is, the greatest common divisor GCD of p and q must be 1, right. So, that if you put that, then out of all this, by the first condition this representation will go out, it is same as this, and by the second condition these two representations will also go out. So, you are left with only one unique representation for 2 by 3. Similarly, if you look at these three, the only unique representation is minus 2 by 3. Right? So, this is also what we know by rational numbers in mathematics, and that is what we are going to represent here in terms of the fraction. Another point to be noted, that a fraction is called proper if its absolute value is less than 1, otherwise it is called improper. So, there is some whole number part in that fraction, in an improper fraction. So, if I have an improper fraction, then I can take out the whole number part and the remaining part I represent as a fraction. So, this is called mixed fraction format. So, 17 by 3 is 5 2 by 3, right. 5 is the whole part, 5 times 3 is 15 plus 2 is 17. So, this is the basic notion of the fraction that we deal with. So, formally speaking, a fraction p by q for our purpose, where p and q are integer, q is greater than 0, p and q are mutually prime, p is called the numerator, q is called the denominator, and if a fraction does not satisfy this condition, then it is called a irreduced fraction. So, a irreduced fraction can be reduced by dividing the numerator and the denominator both by the GCD of the fraction. Right. There are several operations available. For example, reduction by itself is an operator. If the GCD is not 1, then you can make the GCD 1. If q is not positive, then you can make q positive. If p is 0, q can be anything. So, you force q to be 1, and if q is 0, the denominator is 0, then the fraction is undefined. Given that, we have a number of rules of fraction which you know from the arithmetic, like addition, subtraction, multiplication, division, or even remainder. Right. So, by remainder, what you mean is you divide one fraction by the other, first fraction by the second, take the integer part of it, multiply it with the second fraction and subtract from the first fraction. So, this basically is a percentage b is a minus read in the context of the fraction is what gives you the remainder. Here are examples given. So, there are some rules of fraction also, like we know of invertendo, that if you flip the numerator and denominator of two fractions which are equal, then they remain equal. So, we define that to be a flip operation or an inversion operation. Componendo is adding 1 to a fraction, which is basically prefix or postfix operator, increment operator. Dividendo is subtracting 1, so it is prefix or postfix subtraction operation. Right. So, these are very naturally map onto the different operators that we have in our integer domain. So, with that, if we have to now talk about the design of the fraction class, then certainly there will be two members, n for standing for numerator, which is of type int because it can be signed, and d, which is the denominator, we take it as unsigned integer because we said that it has to be greater than 0, it cannot be negative. Right. So, then what are the operations that we will have? Obviously, we will have the usual construction, destruction, copy, construction, copy, assignment, and so on. We can have different unary arithmetic operations, like taking the negative of a fraction, doing a componendo, that is adding 1, subtracting 1. We can do binary operations of add, subtract, all that. We can do Boolean relational operations, that is comparing two functions, less, less equal to, and so on. Certainly, we can do read and write. We can invert a function, fraction, that is flip it, numerator and denominator, we can convert it to double, and so on. So, these are some of the very quickly identifiable operations of a fraction type that we come to, which have close simile in terms of the int class, not in every case. For example, int does not have an invert kind of a functionality, right, but most others are basically borrowed from the int data type. And along with that, we need some convenience functions like GCD and LCM. GCD because we need to check for the validity of whether a fraction is reduced, otherwise we will have to reduce it. LCM is required for adding, subtracting functions and so on, least common multiplier, and we need a reduction operation. These are basically what your implementation is going to need. Right. So, this is your basic design that you identify. So, that is the first step. We have clarified the notion we have decided on the representation, we have decided on the set of operations and their properties that we want to realize. So, with that let me do a first version of the interface design for the fraction. So, I need we have a fraction constructor. Naturally, I need two numbers to construct a fraction. So, I have defaulted both of them to 1. So, that I may not give any parameter, in which case it will give me the unit fraction 1 by 1, which is the default constructor. Otherwise, I can give one the first parameter, or I can give both the parameters. There is a destructor which does nothing, copy constructor, copy assignment operators, these are routine. Naturally, I need a read write function which will take a fraction and write it to the cout. Similarly, a read function which will read a fraction from the cout as a pair of numbers. Right. So, here you can see that at the first go I am not attempting to get into the different operators, I am just identified each and every operation, I am giving it a name for the member function and identifying what will be the signature. Now, up to this point these things are almost generic, I mean irrespective of whether it is a fraction or a complex or any other, you will have similar functionalities. But now we have say I want to do a negate. So, when I decide on an interface member function, there are primarily based on the functionality, there are primarily three things to decide. One is what is the parameter, right. So, if it is a unary operation, then it does not show a parameter as a member function, because the object itself is the parameter on which it applies. If it is a binary operation, then it takes only the second operand as a parameter. The first operand is the object itself on which this member function is invoked, you already know that. So, this is how you decide on the parameters. Then you decide on the what is the return type. The return type typically here is either you have return by value, when will you have that, when that operation computes something which is a new object and your current object is not changing, probably not changing, or it may be changing, but probably it will, the current object will not change and you are having a new object. So, here when I do a negate, say I have a fraction 5 by 3 and I want to do a negate on that. So, I should get a fraction minus 5 by 3. So, this is a new fraction which has to be created. So, I have a return by value and the original fraction should not be disturbed. So, I write a const. So, you will typically see that if it is not necessarily always, but typically when you have a return by value from such member functions, you will that member function should preferably be constant. So, these are whereas, if I do component, I am adding 1 to the fraction itself. So, I want that fraction itself to change. Therefore, neither can it be const nor can it return a different fraction, it has to return itself. So, it has to return by reference, right. So, this is the basic consideration that you do for designing. So, for addition, subtraction, all of them are const member function, because you do not expect the parameter to change because of that. All of them return by value, because we expect the result to come as a returned object, as a new object. Obviously, you can do equality, inequality, all comparison checks. Trivial to say that they are all constant member functions, because they should not change the fractions that they are comparing. They will all return bool, quite straightforward. If I invert a function, then I am sorry, if I invert a fraction, I take 1 by that fraction, then I will get a new fraction. So, it is returned by value and it is a constant member function. Double is a special member function I am saying, which will take the current fraction and will return its value in as a double number, right. This is kind of a conversion fraction. In addition to that, we define some unity fraction and 0 fraction, because they will come in ease for writing the code. And we have the support function for GCD, LCM. These are not dependent on your fraction class. So, they are static members, and you have a fraction, you have a reduce which does reduction on the current fraction object to bring it to the normalized reduced form. Remember that these parts, these members are not a part of your interface, that is, the user is not going to use this. So, you will typically have them as private, and you may not mention that in the part of the interface, just as together I have written it here. So, having done that, the next is to, so I have a design, now all the interface. So, now I will have to implement in terms of the two members, data members, n underscore for the numerator and d underscore for the denominator. So, these are very trivial implementations. For example, this is a constructor which has to construct and do a reduce. You will see something interesting going on here, because when you call the constructor, the denominator is int. So, it is possible that I call the constructor with say 2 minus 3, but I cannot have a fraction 2 by minus 3, because the denominator is a signed number here, whereas in my representation is an unsigned integer, d underscore is unsigned. So, I cannot take minus 3 and put it to d underscore. So, what I have to check before the data members are initialized, that if d is negative, then I have to flip the sign, and if d is negative, then I have to flip the sign of n also to keep. So, if it is given as 2 minus 3, eventually I make it as minus 2 3 and construct, and then do the reduction. So, that if I have 4 minus 6, then I actually will get minus 2 3 in the representation. There is nothing great in terms of the copy constructor, because there are no resources, destructor or copy assignment operator, they are routine. In terms of writing, you will write one component and then decide and write a slash to write the second component 2 by 3, but putting some conditions that if the numerator is 0, then do not write it as 0 by 1 or 0 by 5, it is better to write it as 0, or if the denominator is 1, then it is a whole number. So, it is better to write just the whole number. So, coming to negate, you just have to flip the sign of the numerator. In componendo, you have to just add 1, you already now can see that why we had this static constant fraction. I can add unity, I can subtract unity, and I can very easily realize these different member functions. The add function you can go through carefully, taking the LCM and so on, but it is exactly the formula as we have already given in the section of operations. You can, so that is just coded, we will give you this. You have a new fraction created as a sum of the two fractions, and you return that. Subtract you can write in a similar way, but as a very compact way to write is you can negate f2, that is f1 minus f2 is same as f1 plus minus f2. So, you can just negate and use the add, which makes the code more compact and readable. Multiplication is simple, so is division. I am again using invert to use multiplication for getting division, and this is the remainder. You will have to follow that formula for this. There is nothing great in terms of C++ here. Similarly, the comparison operators are very easy. Equality and inequality can be checked directly, and for less or greater you can use the subtract operation and see the sign of the subtraction. Okay. And you can see that once you have some, like this is one operation you implement, this is another operation you implement, and this is the one, the other three you can implement in terms of, actually you may not implement this also. If you implement 2, then everything else can be done as a combination of them. Similarly, for invert, you have to remember that if d is 0, then you cannot invert a 0 fraction. So, you have to throw an exception. You can convert to a double and so on. So, this is a pretty straightforward implementation. This is just the code of GCD, LCM, which is routine code, and this is the reduce. That the reduce reduction tells you that if d is 0, then it is an error. If d is negative, then you have to flip the numerator and as well as the denominator. If n is 0, that is numerator is 0, you have to force denominator to be 1, and if they are irreduced, that is they have a GCD greater than 1, then you have to take the GCD and divide both. So, this is a whole reduction process which is encoded in this. Having done that, the next thing you need to do for a UDT is to generate a test. So, in a test what you do, you write every operation that you have written down, you write down sample cases for that. So, here is a sample case to construct a function with 2 parameters, fraction with 2 parameters, with 1 parameter, with no parameter, a fraction by copying, and so on and so forth. Right. Similarly, you are trying out negate, preserve, componendo. So, you just keep on doing each and every operation and write a code and generate the output and see whether that is being satisfied, that is being printing correctly. So, these all tests are written to actually be positive, pass, and what you see here, you have to trace that program along with this output to be able to see that you are getting each and every output as you are expected. So, this is our first version of the design, and we had promised that we will refine it and use operators. So, let us see the context. Suppose with this version I take an example of 3 fractions f 1, f 2, f 3 that I have defined, and f 4 is given by this expression, right, which actually turns out to be this value. How do you write it in this design? Turns out that it is such a expression, horrendous looking, right. You can get lost any time in terms of using the operator name, parenthesis and so on, and it is very error prone. And that is the motivation for you to jump to version 2, where the improvement that you do is for every member functions that you have used, try to identify what is the appropriate operator that can be used. So, naturally for write and read this is trivial. So, for sorry, these names are swapped, I will correct them. So, preserve is a positive, negate is the negative, then you have the pre-increment which is componendo, then you have dividendo. Incidentally, you also have post increment, post decrement. So, those can be called lazy componendo and lazy dividendo. But what is more interesting is you can have all your addition, subtraction, all these operations now written in terms of operators. And just to remind you on whether they should be member function or they should be friend function, just recall that the shortcoming of being a member function is that the first operand has to be a fraction type. Now, our constructor here is explicit, which means that we will not allow to take an integer and implicitly convert that to a function, fraction. So, obviously, the first member is a fraction can be a very good assumption, and therefore, we do not provide the friend form of the operators, which you may provide, there is no harm, but this is you can here it just suffices to have member function operators overloaded for your addition, subtraction, binary operations. Then you do have your advanced operators where you assigned x plus equal to y, meaning x assigned x plus y and so on, your relational operators and so on. So, all that I am doing is I am just replacing the member functions that I have already designed by identifying the proper operator which can be used in this case. So, I have this exclamation for negate, I have operator double for the conversion and so on, and I have mapped reduce to, this is little unnatural because you do not have a notion of reduce in int, but I have mapped the dereferencing operator because kind of it takes content, dereferencing operator takes content. So, reduce is taking out the proper content. So, on this, but since this is not on the interface of your design, you may just retain the name reduce also, because users will never use this, and there are several other operators which will not get mapped like bitwise operators or shift operators and so on. So, next are just replacing the implementations, and as you will have to go through this, try this out thoroughly, you will see that several of them are just name replacement, but several of them particularly when it comes to say writing this operator, operator subtraction, or writing say operator division and all that, you will find that your even the expression of implementation would be much easier, right. Go through this and you will have a good sense of this, and you can see that how in single line, in just 2 lines you can write the advanced assignment operators, how quickly you can write the Boolean, the relational operators and so on, and everything is now in terms of operators as of your int type. So, this is your complete implementation. Go through that, try this out, and again run the similar test utility to test out if things have been properly implemented. Of course, the expressions will now change. For example, now earlier you were writing negate f1 dot negate, now you write minus f1, you are writing say f1 dot component, now you are just writing plus plus f1 and so on. So, things become more algebraic in nature, and you can have a complete test application based on that through which you test, and this is the total application I have given here, and as you test you will be able to get this output. Try this out and you will see that very clearly. Now, there are one thing which you might want to also test is what happens if you do a failure, if you have a failure. For example, what if somebody tries to construct a fraction with a denominator which is 0. So, naturally those things will throw in your code. So, to try them you have to use the try catch block and then see that actually whether those messages are being caught. So, here are examples of constructing with a denominator 0 or trying to divide by the 0 fraction or trying to take remainder with the 0 fraction and so on. And you will see that all of these will also pass because they are throwing the proper messages. Now, before we conclude, let us get back to the example we took after version 1, that what if I have 3 fractions and just an apparently not very complicated algebraic expression with these fractions, and version 1 led to such an expression. In version 2 it reduces to exactly as you write the algebra. That is the key advantage of being able to overload operators with proper meaning, and that is how your version 2 will turn out to be a true UDT, because it is now allowing you to use fraction just like you use the int, float, these kind of types, right. So, in this part of the tutorial we will continue in the next tutorial also show you with building of other UDTs, but we have discussed about the general issues in building a data type and why we need to build that, and we have shown how to build a fraction data type by iterative refinement. Thank you all very much for your attention. See you in the next module.